What is electroweak interaction? What if two of the most fundamental forces of nature were actually different faces of the same phenomenon? This question leads us directly to one of the most important ideas in modern physics, the electroweak interaction. The electroweak interaction is a fundamental force that unifies two forces we encounter everywhere in the universe, electromagnetism and the weak nuclear force. At first glance, these forces seem completely different. Electromagnetism governs electricity, magnetism, light, and almost all everyday technology. The weak nuclear force, on the other hand, is responsible for radioactive decay and the nuclear reactions that power stars. Yet, at extremely high energies, these two forces merge into a single unified interaction. This idea was developed in the 1960s by physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their theory showed that at very high temperatures, like those that existed just moments after the Big Bang, electromagnetism and the weak force behave as one. As the universe cooled, this unified force split, creating the two distinct forces we observe today. The electroweak interaction is carried by fundamental particles known as gauge bosons. Electromagnetism is mediated by the photon, while the weak force is carried by the W, and Z bosons. A key difference between them is mass. Photons are massless, allowing electromagnetic forces to act over long distances. The W and Z bosons are extremely heavy, which limits the weak force to very short ranges. But why are some force carriers massive while others are not? The answer lies in the Higgs field. Through interaction with this field, W and Z bosons acquire mass, while photons remain massless. This mechanism was confirmed in 2012 with the discovery of the Higgs boson, providing strong experimental support for electroweak theory. The electroweak interaction is a core part of the standard model of particle physics. It helps explain how particles gain mass, how stars produce energy, and why certain particles decay. Without it, our understanding of the universe, from the smallest particles to the largest cosmic events, would be incomplete. In short, the electroweak interaction reveals that nature is far more unified than it appears. Beneath the surface of separate forces lies a deeper, elegant connection that shaped the early universe and continues to govern the fundamental behavior of reality itself.